Welcome to the debate. Today, we are tackling really the core engineering and philosophical conflict defining the future of automated driving. It's this fundamental disagreement between pursuing a pure vision system versus, well, relying on a multi-sensor fusion architecture.
Right. And this isn't just about, the hardware list. It goes much deeper, reflecting these really opposing philosophies on safety, on scalability, and frankly on the path we actually need to take to get to level 4 and level 5 autonomy.
Exactly. This divergence, it's critical because it separates those who maybe lean on established safety-critical engineering traditions, things borrowed from aerospace, for example, from those who believe a software-first, data-centric approach can, well, overcome physical limitations. So the central question, I think, defining this split is pretty straightforward. In developing truly safe and scalable automated driving is the approach that prioritizes data consistency and AI simplicity. That's the pure vision approach. Is that strategically superior to the approach prioritizing physical redundancy and sensor complementarity, which is, of course, multi-sensor fusion?
And I'll be arguing that the absolute core requirement for reliable and robust safety is that physical redundancy, rooted in those, time-tested safety-critical engineering principles. And that, to me, necessitates a multi-sensor fusion foundation.
And I'm going to argue that pure vision, driven primarily by superior AI and leveraging this, frankly, unparalleled data engine, is the strategically sounder path. Why? Because of its fundamental simplicity, its speed of iteration, and its massive potential for commercial scale.
Okay, that's a strong strategic claim, I grant you, but let's maybe start with the foundational logic of safety itself. My core thesis, it really rests on a simple fact. No single sensor is infallible. Period. Whether you're talking camera, LiDAR, radar, each one has inherent, known weaknesses. Therefore, when you're talking about a moving vehicle responsible for human lives, the industry standard, the one we've learned the hard way in other fields, mandates physical redundancy, specifically what we call a fail operational design.
Okay. I appreciate the historical context, aerospace engineering, where redundancy is absolutely king. But I think that analogy starts to break down a bit when we introduce modern machine learning models trained on literally billions of miles of visual data. We actually believe that increasing the number of sensors leads directly to what you might call sensor contention, or maybe better put, sensor confusion.
Confusion? How so? What do you mean by contention?
Well, when you fuse multiple streams, camera, LiDAR, radar, they inevitably provide potentially contradictory data, even if each stream is technically correct within its own physics, right? So for instance, the LiDAR sees a perfectly measured 3D depth map, but the camera sees semantic evidence, road signs, paint that might contradict that geometric map in subtle ways. The AI is then forced into this position of having to resolve that conflict.
Okay.
And that ambiguity, that forced resolution, it causes the AI to hesitate, or even worse, potentially make an incorrect decision because it's constantly having to figure out which input to statistically trust more in that specific microsecond. In our view, that fundamentally reduces the overall safety and fluidity of the system.
But isn't the whole point of fusion aiming for complementarity? Actively mitigating known weaknesses, not creating conflict. That's the entire design philosophy behind it. We know cameras provide unparalleled semantic information, color, text on signs, lane markers. That's invaluable.
Sure, semantically rich, yes.
LiDAR provides precise 3D geometric depth. Crucially, it's unaffected by ambient light or tricky shadows where cameras can struggle. And then radar, well, it offers superior penetration in genuinely adverse weather, heavy fog, pouring rain conditions, where cameras, let's be honest, can become pretty useful. Plus, radar gives you highly accurate speed measurements, Doppler effect and all that.
I think it rarely works out quite that cleanly in the real world, though. The edge cases of fusion are complex.
But fusion ensures that if one sensor fails, let's say a camera is blinded by a low sun, total whiteout, or gets splattered with mud, the others provide immediate backup. They maintain the perception integrity of the system. And that physical backup, I would argue, is simply non-negotiable if you're serious about achieving certified safety-critical levels like L3 and especially L4.
I do understand the appeal. That belt and suspenders approach is intuitive. But this is where we see the core divergence. safety achieved via data consistency versus safety achieved via fault tolerance. Fusion advocates, as I see it, attempt to resolve that inherent data conflict using, yes, complex mathematical models, Kalman filters, Bayesian inference, you name it. They rely on calculating these acceptable tolerances. Sometimes folks call them OK bands, right? These ranges within which the sensors are basically permitted to disagree before flags are raised.
And what precisely is wrong with statistically reconciling uncertainty? That's standard engineering practice in complex systems.
I guess I would frame the reliance on constant statistical reconciliation more as patching over a fundamental design flaw rather than solving the root problem with elegant simplicity. The safer, simpler philosophy from our perspective is to eliminate those conflicting data sources entirely, which is exactly why pure vision systems deliberately choose to eschew complex radar and LiDAR inputs. If you eliminate the source of the conflict, you ensure judgment consistency for the AI.
I'm sorry, but I just don't buy that probabilistic methods are mere patches. Fusion techniques aren't just, averaging out noise. They are sophisticated engineering solutions. They actively model and dynamically weight the uncertainty of each sensor in real time. So for example, if heavy rain is detected, the system instantly lowers the weighting given to the visual camera input because its certainty has obviously dropped due to distortion from the raindrops.
Right.
And simultaneously, it increases the weighting given to the radar input, which is known to be highly robust in precipitation.
But that complexity, that dynamic weighting, it adds layers and layers of code, potential failure vectors, calibration nightmares.
Conversely, it generates a statistically more accurate and, crucially, more robust comprehensive estimate of the world than any single sensor possibly could provide on its own. Your philosophy, with all due respect, creates a dangerous single point of failure risk. If the world is truly designed for human eyes, as you often argue, then the AI's visual system must be proven to be as robust or even more robust than the human eye-brain system. And frankly, that has not yet been demonstrated across all conditions, not even close.
Which, okay, leads us back to the strategic choice then. If the world is designed for human eyes, then solving the visual problem with an AI that effectively mimics and ideally enhances the human visual system is the only path to achieving general autonomous driving, driving anywhere, anytime, without the crutch of geofencing. Concentrating resources on optimizing AI specifically for vision, rather than scattering R&D funds across disparate hardware systems and their integration headaches, accelerates that ultimate goal.
But general autonomy requires robustness, especially in extreme conditions and edge cases. And this is exactly where pure visual systems empirically reveal their performance vulnerabilities. We've seen clear data, published data, showing that pure visual performance significantly declines, sometimes drastically, in extreme weather. Heavy rain, dense fog, even certain low-light scenarios can be major problems.
That's a known challenge of physics, yes. Light doesn't travel well through fog for cameras or eyeballs.
It's a challenge that matters in real-world safety, though. Reports have shown these systems sometimes have to reduce their maximum speed dramatically or even disable basic cruising functions entirely when the camera lenses are obscured by heavy rain or glare. And furthermore, we can point to regulatory investigations, NHTSA and others, which cite systematic failures often linked back to semantic misinterpretation or challenging lighting conditions. We're talking about serious events like running red lights or failing to properly detect and respond to traffic control devices like cones or barriers.
Okay, running a red light due to semantic failure. That is absolutely the nightmare scenario the public rightly focuses on, and we acknowledge the challenge. But let's be fair here. The multi-sensor industry mainstream also faces significant issues. LiDAR accuracy, for example, degrades due to scattering effects in heavy rain or snow. And radar, well, it notoriously suffers from poor angular resolution and really struggles with detecting stationary objects reliably at highway speeds. Those aren't trivial problems either.
But the fusion system has redundancy baked in. If the LiDAR beam scatters, the camera and radar still provide inputs.
If the camera is blinded by glare, the LiDAR and radar maintain that crucial geometric integrity and motion tracking. That's the point.
And we argue we mitigate these environmental risks not by adding more costly, complex hardware, but through intense, focused investment in advanced AI. This is really where the sheer advantage of the data engine comes into play.
Such as? Can you be specific about how software is meant to overcome these fundamental physical limits of a camera?
Sure, we are talking about increasingly sophisticated AI architectures, like occupancy networks, for instance, and also heavily leveraging the transformer model, which has shown incredible power. An occupancy network, it's explicitly designed to model the 3D space around the vehicle by inferring what is free space and what is occupied space, rather than relying solely on identifying and drawing precise geometric bounding boxes around known objects.
Okay.
This helps the system handle unstructured stuff like road debris, a plastic bag blowing across the road, construction zones, far better than older systems could. It helps compensate for situations where a simple 2D imagery might struggle with accurate depth perception on its own.
And the transformer architecture?
Right. The transformer architecture allows the AI to consider the entire scene context almost simultaneously, inferring complex relationships between objects and better constructing precise 3D depth from the 2D imagery it receives. This capability allows the software to essentially understand the physics and context of the world more deeply. It effectively compensates for the inherent physical limitations of the camera array, but it requires massive, real-world data training. We view this as a necessary investment in building generalized intelligence, not just, patching a sensor problem.
But if I may, those incredibly advanced, computationally expensive solutions are required precisely because you chose hardware that lacks native 3D depth perception from the outset. Those semantic failures you acknowledge, running lights, misinterpreting static objects, those are exactly the kinds of failures that a simple geometric confirmation from a LiDAR or a robust speed reading from a radar could potentially prevent as a kind of guaranteed fault protection mechanism. It's a safety net.
Well, that leads us directly then to the strategic reality of adoption, the cost equation and achieving global scale. The pure vision route is, we believe, fundamentally a superior commercial strategy. Why? Because it dramatically lowers the bill of materials, the BOM cost, by removing expensive LiDAR sensors and most, if not all, high-frequency radar units.
That initial cost advantage is eroding, though, wouldn't you say?
But the current low BOM makes pure vision instantly scalable for the mass consumer market today. Our strategy is focused on rapid iteration, getting the hardware out there quickly, even if the software isn't fully L4, L5 yet. This allows for what you could call an overnight global scale-up via seamless over-the-air OTA updates across a fleet potentially numbering in the millions of vehicles. That scale creates an incredibly powerful, self-reinforcing data engine that, frankly, capital-intensive, geographically fenced robo-taxi operations like Waymo or Cruise just cannot match in terms of data velocity and diversity. That data moat, we think, is the winning strategy for achieving universal autonomy.
I absolutely appreciate the undeniable power of scale. Nobody disputes that. But that initial cost advantage of pure vision, it's rapidly losing its potency. LiDAR prices are already falling incredibly fast. They're projected to reach the, $200 to $500 range per unit very soon. That means the multi-sensor approach is becoming commercially viable for standard consumer cars, not just premium models or taxis.
Those are still significant added costs, potentially thousands per vehicle when you factor in integration, calibration complexity, compute requirements.
Perhaps, but you seem to be ignoring the hidden costs of the pure vision approach. You're essentially trading hardware capital expenditure for massive software capital expenditure. The gigantic, persistent R&D investment required for that level of AI development, plus the specialized computing infrastructure needed, things like Dojo, just to try and force the camera to do what other sensors do more naturally, that is definitely not cost-free. It's a huge ongoing bet on software R&D.
We see it as an investment in fundamental intelligence that pays dividends across the entire connected fleet,
improving safety for everyone simultaneously.
And critically, I think this discussion most acknowledges the regulatory framework. Look at the regulated Level 3 systems that have actually successfully received approval for public use, like Mercedes' Drive Pilot system in Germany and parts of the US. They were certified precisely because they adopted a full, redundant hardware architecture, explicitly including LiDAR, alongside cameras and radar. This strongly suggests, to me at least, that the regulatory path to viability for safety-critical levels L3 and beyond will ultimately demand that physical redundancy, regardless of how smart or advanced your vision-only AI becomes. Regulators, at the end of the day, demand a verifiable physical backup for potential failures.
I hear that, but I still maintain that the most efficient, the most scalable, and the most AI-centric approach is to minimize the hardware complexity, maximize the AI intelligence, and use the sheer data advantage from a massive fleet to converge on the generalized intelligence needed for true universal autonomy. We genuinely believe the software solution is ultimately the only generalized solution that scales globally.
And I must reiterate the fundamental engineering consensus built over decades. Safety demands verifiable redundancy. While pure vision certainly offers compelling scalability and, yes, a powerful data moat, established principles confirm that physical backup systems, LiDAR and radar, which provide truly complementary strengths, are, for now, indispensable for ensuring system stability and passenger safety, especially in those critical edge cases and adverse conditions that define real-world driving, not just sunny California highways.
It's clear then that divergence in sensor philosophy is ultimately a competition and risk management philosophies. It's a highly sophisticated debate between leveraging software evolution and immense statistical power to try and overcome physics versus relying on physical redundancy to guarantee absolute fault tolerance, or as close as we can get.
Indeed, and the material we've looked at strongly suggests the final outcome will really depend on which approach can achieve both massive scale and profitability, while at the same time satisfying those stringent, non-negotiable regulatory safety standards that exist to protect the public. It remains a truly fascinating and critical tension within the entire automotive and tech industry.